Welcome back to the Shopman to the channel. The last few videos that I've published here on the channel have been centered around this dividing head and trying to get it set up to do some gear cutting on the horizontal mill. This is something I have never done before, and I have been excited about being able to do this for quite some time. Not for any particular reason. I don't have any gears I need to make, but I guess as a hobby machinist, it would be cool to have that ability, should the need arise. I do want to back up a little bit just to kind of level set on what it would take to manually cut a 22 tooth gear on a milling machine with a dividing head. Well, the first thing you'd have to do is look up on a chart or do the calculations to figure out what hole pattern or dividing plate you'd have to use in the dividing head. So let's say, for example, I'm going to cut a 22 tooth gear. The chart for that says I need a 33 hole pattern dividing plate. This one right here has holes for 21, 23, 27, 29, 31, and 33. The next thing I have to do is adjust the handle here, my handle crank, so that the pin is going to drop into one of the holes on that 33 pinhole pattern. The other thing I need to do is make sure that the dividing plate itself cannot spin. So there's this little locking pin that's on an eccentric, and I just need to rotate it till it fits into one of the holes on the back of the dividing plate. Next, I need to reset these sector arms. There's a set screw here that you can't see from this camera angle. I'm loosening it here, and that'll let me spread these two sector arms apart. Now, to cut a 22 tooth gear, for each tooth, I need to rotate this handle one complete turn and then 27/33 of a turn. The math for this isn't all that complicated. Remembering that for a 22 tooth gear in 360 degrees, that means each tooth is separated by about 16.4 degrees. And with the 40-to-1 ratio of the dividing head, that means one full turn of this handle will result in 9 degrees of rotation. And in this case, if I rotate the handle now 27/33 of a rotation, that results in a rotation of the front of the chuck by 7.4 degrees for a total of 6.4 degrees, which is exactly what we need for each tooth of a 22 tooth gear. The setup for this is not difficult. It's just that you have to either understand how to do the math or you use the charts that are generally provided with these dividing heads. And that's how I chose this particular dividing plate and knew how many holes to actually turn the handle. So now I have my sector arm set up where there is 27 holes in between the two arms. So every time I want to make a rotation to cut to the next tooth, I just need to pull this handle, rotate it one full turn, and then keep rotating it until it ends up right at the next sector arm. This keeps me from having to count these holes for every single tooth. Now, for a 22 tooth gear, that's not terrible, but if it was 60 teeth, that might be a bit tedious. Even as it is, doing all this rotation, moving the sector arms, etc., it is a fairly tedious process. And this is pretty simple. It's only one turn. I don't have to keep track of multiple turns. If this was a more complicated gear, or rather different number gear, I could be rotating this thing 3 or 4 times in order to get the result that I want. The upside is there is a better way. I love doing manual milling, but I don't mind adding a little bit of technology in it to make it a little bit easier, and that's where the DRDRO comes into play. I have all of the parts in place now. I'm getting the dividing head mounted to the table of the K&T, But there is one last piece of information, or one last thing I need to create, and that is I need to determine the gear ratio, I will call it, that I need to tell the DRO about this specific setup. Now, the servo motor that I'm using has a resolution of 10,000 pulses per revolution. In other words, the rotary controller will need to send it 10,000 pulses for it to rotate 360 degrees. So it's got a fairly fine resolution on it. However, it might actually be too fine, and I need to make some adjustments and do some math in order to figure out how many pulses I need to send the servo so that the dividing head chuck does one full 360 degree rotation. Well, as I mentioned, out of the box, the servo has a default resolution of 10,000 pulses per revolution, but I think that is actually too fine. That might be a problem for the rotary controller to keep up for certain operations. So I was given some advice, and that was to set the internal ratio on the servo controller to 1:5. And what that means is now the servo only needs 2,000 pulses to do a 360 degree rotation. To further calculate the pulses per revolution, I need to add in the ratio for the drive pulleys. Now, I added a 30-tooth and a 40-tooth drive pulley, so that gives me a 3:4 ratio, which now takes the pulses per revolution up to 2,666 and 2/3. The output of those two drive pulleys is the input to the shaft of the dividing head. Now, the dividing head has a 40-to-1 ratio, which means I now need 106,666 and 2/3 pulses in order for the chuck on the front of the dividing head to turn 360 degrees. However, the rotary controller in the DRO does not like decimal numbers. I need to convert that to an integer. So by using a multiplier of 3, that means I will send 320,000 pulses to the servo, and it will rotate 1,080 degrees, or 3 times. Over here in the settings for the servo in the DRO, there's several values. The two I'm interested in are the gearing ratios. You can see here for the numerator and denominator, I have them set to those calculated values of 1,080 to 320,000. For my test gear, I'm going to cut a gear that's 22 teeth. So I'll enable the servo, and I'm going to change the divisions here to 22. I'll reset the angle readout to 0. And if I index the rotary controller, it should turn the dividing head. And it did. However, there was one thing that I do need to change. The dividing head rotated in the opposite direction. I want to have that handle rotate clockwise. So I'm going to go back in here into the servo settings, and I'm just going to change the numerator ratio to a negative 1,080. Much better. I prefer it running in the direction that it was intended to. So on to the next step. In order to cut gears, you need gear cutters, and I didn't have any. So I reached out to my friend Tom from Tom's Rabbit Hole. Tom is a master at making gears, and I knew he'd have some good answers of what I should look for. Told him what I was doing, and he offered to let me borrow this set of gear cutters. Now, these are for a diametral pitch of 16 with a 14.5 degree pressure angle. There are 8 different cutters in this set because each cutter is used for a different range of tooth count on a particular gear. Also sit along this arbor, and I needed this arbor because my arbors are imperial, which means they're all 1 inch or more. And these import involute gear cutters are metric bores. They're all 22 millimeter, and they're not going to fit on anything that I have. So Tom had made up this arbor that's got a 1-inch shank on it, and that'll be just fine. I'll be able to mount this shank into a 1-inch tool holder and then mount that into the spindle of the Kearney and Trekker. Since I'm going to be cutting a gear that's 22 teeth, I'm going to need this particular gear cutter here, which is used for cutting gears that are between 21 and 25 teeth. I'll take off this nut here on the end of the arbor. I won't need these spacers. I'll take off the main spacer, and then that exposes the key. I'll mount the cutter that I want to use, making sure, thinking in my head, is this going to turn the right direction? It's engaged with the key. I only need one spacer here, I think, so we'll put the one spacer on. We'll leave these other ones off and then screw on the nut for the end of the arbor. I have this 1-inch tool holder with a 40 taper on it that this should mount up into just fine. Since this is my first gear ever, I don't want to take the chance of either dulling or breaking any of those gear cutters that Tom has let me borrow, so I'm going to use this piece of plastic. I suspect that this is probably Delrin. I'll get this material here chucked up in the lathe so we can start machining these blanks. The end of this thing is a pretty rough saw cut, so I'm going to come in here with a lathe tool and face this off flat. I want to give it just a little bit of support here. I am going to be turning down the OD of about an inch or so of this, so we'll drill it for some tailstock support with the live center. Well, based on some calculations, in order to do a 22-tooth gear with a 16 diametral pitch, I need to have my blank to be about 1.5 inches in diameter. So I need to do a little bit of turning here in order to reduce the overall diameter of this. I'm going to give myself a little bit of room, so we'll go down to about 1.5 inches. I'm going to eventually need to mount the gear blanks on an arbor, so I might as well go ahead and drill a hole through these now. I am going to make 2 gears, because what's the fun of making a gear if it doesn't have a mate? So I'm going to drill about a 1/4 of an inch hole through the center. I was thinking a 1/4 of an inch might be a little bit too small, and I have some 5/16 inch dowel pins, so I'm going to open this a hole up a little bit and give me a little bit more room here, maybe make it a little bit better to have a larger diameter on the arbor. So I've got my cutoff tool here in the tool holder. The only time I get to run my lathe at full speed using a cutoff tool is when I'm cutting plastic. So I've moved it down a 1/2 of an inch, and I'll go ahead and cut off 2 blanks. I might as well move right into making an arbor for these blanks. So let me get this piece of plastic out of here, and I'll chuck up a piece of material out of the scrap drawer. This piece of material, I remember using it years ago when I was testing the taper between the, or should I say the offset between the tailstock and the spindle, and adjusting it if it was cutting a taper. But this end here still has a little bit of the original mill scale on it. I just want to clean it up a little bit. This will be the end that will sit in the chuck on the dividing head. So I just want to have a decent clean surface that's doesn't have any area that's too proud of the rest of it. Well, that should be good enough. It doesn't have to be pretty, it just has to be functional. So we'll flip this around so I can machine a spigot on it for the blanks. When I'm machining the gears, I am going to be using some tailstock support, or footstock support as it's probably called. And it is going to have a center in the end of the spigot, although this right here is kind of big and I can't say for certain that it's truly centered. So I am going to go ahead and machine this existing center off before machining a new one, which I want to use a smaller center drill than what it looks like this one was machined with. The face is nice and cleaned up. I'll come in here with a center drill and just drill a shallow center, just enough to have a little bit of tailstock support when I'm machining the spigot, as well as footstock support when I am machining the gears on the horizontal mill. Use a little bit of anchor loop here to get things started. I want to loosen the chuck jaws here so I can extend the stock out from the jaws about 2 inches. I need about 2 inches coming out because this spigot's going to be about 1.5 inches or so in length. I'm touching off on the end of the material here just briefly so I can reset the zero on my travadial, and I'll move in 1.5 inches to where the shoulder is going to be for this arbor. Now I need to machine this down to 5/16 of an inch, so it's going to take a few passes, especially with this lathe being only 1.5 horsepower and being belt driven. I could take maybe up to about a 50,000 step the cut before this lathe would start to bog down a little bit and be challenged. So I'll start slow and we'll see how deep I can go as I progress. Well, that's a really nice surface finish, but I'm going to swap tools here to one that is going to let me get a little bit tighter into that live center. I realized after taking that first cut that tool would not get me in close enough to the center where I'd be able to actually machine it down to that 5/16 of an inch. This tool is much better for me in that regard. Well, we are almost to size. I'm going to take one more quick pass and then machine a little bit of an undercut at the base of the shoulder, as well as to clean up the face of it so the gear blanks sit on it nice and square. And then a quick chamfer here just to ease that sharp edge. Putting the two gear blanks on here just so I can be sure as to how far I'm going to need to thread the end of this spigot. I am going to thread this with a die and a die handle. So we'll start with a little bit of anchor lube here to make sure everything goes smoothly. One of these days I like to build one of those tailstock die holders, but it's just down on the priority list. There's too many things in front of it, so we'll do this by hand. What I do like to do is take the drill chuck with the jaws completely retracted, and I use that to apply a little pressure to the die handle here. That kind of helps keep it square and then still gives me a little bit of aid in pressure into cutting the threads. Well, I think those threads would probably work just fine, but I think I want to add a few more just in case. Use a file here just to deburr the tops of these threads, and then I'll come in with a chamfer tool to chamfer the end of this since I forgot to do it before I started threading. Well, that nut fits on there just like it was supposed to. Well, I think I'm about ready to start cutting some gears. So I'll get this arbor mounted up in the spindle. I need to set the gear cutter so it's directly in line here with the arbor, so I'm cutting the correct profile gear. And there's a few ways you could do this. You could certainly try to do this by eye, but considering the size of the gear, I would like to try to get it as close as possible. So much in the same way that you would use your DRO to find the center of a part on a milling machine, on a vertical milling machine, I'm going to do the same thing here on the horizontal mill. Well, I have the table up as high as it will go without hitting the arbor, and I've got the spindle running at a fairly low speed, and I'm just taking a piece of paper here and holding it in between that spigot and the milling the gear cutter. And when that grabs, that tells me I'm within 0.03 of an inch of the side of that gear cutter of hitting the spigot on the arbor. So I'm going to set the 0 on my DRO. I'm going to lower the table down now and move the gear cutter to the other side of the spigot. I'll raise the table back up to the same location it was before. I did set a 0 on the DRO for where it was. And I'll perform the same exercise with the paper, except in this case I will set the half function for the y-axis, the y-axis on the DRO. Now I can go ahead and lower the knee and adjust the saddle until the DRO reads 0, which should put the gear cutter directly over in line with that spigot. I'm going to go ahead and cut both of these gear blanks at once. I'll put them both here on the arbor, and I've got a washer and a nut. We'll tighten these down. Then I'll bring in the footstock to give it that tail support. I'm going to go ahead and raise the knee here. I'm going to do the same paper trick here until the gear cutter snags it out of my hand. That puts me within a few thousandths of the top of the blank. I am going to take this all in one cut. So once I set the Z height 0 here, I'll back off and raise the knee. I think it was about 139 thousandths, gives me full depth of cut. Well, I think I am all set to cut these gears. So we'll get the spindle started, and I'll use the power feed. I think right now, this is a little bit fast. I think I'm going to go ahead and slow this down, and then we'll set the travel speed to about 5 inches per minute. Unfortunately, when I was changing the speed of the milling machine, I realized the camera had stopped. So I had slowed down the RPMs here to be a little bit more reasonable, and I ended up cutting the first 2 teeth not being on camera, which is kind of disappointing. I kind of wanted to capture all that in camera, but here we are taking, I think, the 3rd pass. That pass finished, I can reverse it with the rapid. I'll index it to the next tooth location, automatically moves it the correct number of degrees, and I can take another pass to cut the next tooth. That's the last pass. That's all 22 teeth now cut. I'm going to index it, back to the beginning and run the cutter through it just to be sure to see if it's making any additional cuts. And it doesn't look like it is. It's not taking off any more material. At least I can't tell from this vantage point, which tells me that the calculations were correct. I've got the gear ratio set properly to give me the rotations I'm expecting. Well, this thing is kind of a mess. I'm not sure that this is actually Delrin because I don't remember Delrin creating this kind of burrs, at least not when I was using it for something else. It does machine nice, whatever it is, but man, it's kind of a mess. I'm going to have to spend a little bit of time here trying to get this cleaned up. Well, I've got it back over here on the lathe because I want to cut those, nice little chamfers that you see on the edges of gear teeth. And watching this video back and also experiencing it in person, I wish I had not done this because, again, this machining raised a whole bunch of burrs, and I think it was kind of not worth it. So I'll got one side of this thing chamfered. I'll flip this around, chamfer the other side of this one gear, and then do the same to the other gear. Well, these things ended up quite a bit of a mess. I mean, they're just loaded with these little burrs. I could be here forever with the file, but I think what I'm going to do is I'm going to be a little bit more mechanical on this and take them over to the wire wheel and clean them up. I know that's going to end up causing a little bit of damage to this plastic, but, this is a test gear, so I'm not too worried about it. I did clean these up on the wire wheel, and it did do a little bit of damage to the top of the tooth profile, but again, I'm not too worried about it. But I am happy with how they turned out. Yeah, I mean, I just cut my first two gears. They're fake gears. They're plastic gears. I guess they're not really fake gears, but they're not used for anything. I would like to maybe make a little mount for these, for them to sit on. Maybe put it on my shelf in my office, but not too worried about it right now. Maybe if I can find some time over the weekend, I'll give that a shot. But yeah, for now, I think I'll call this a success. Yeah, definitely a success. I could not be happier with how this turned out. I'm anxious to cut some real gears here one day. And I do want to give a shout out to Stefano, who invented the DRDRO. He's continuing to improve it with software updates. And we've even been discussing on his Discord some other ideas about how we can make even more improvements to it. There's quite a few people that are starting to be interested in this project. He's got a friend, Luke, who lives in Malta, who has, I think, 4 or 5 DRDROs on different machines. And then if you watch Rotary SMP, Mark, he is getting one mounted on his surface grinder. I think he's going to be interested in doing, a servo motor setup too at some point. And I think it'll be really cool, and I'm excited to see what Mark comes up with. I don't have any real need for a gear project just yet. However, the next thing I want to do with this, I'm not sure when I'm going to do with it, is I want to look at how I can make a helical gear like this one here in the vertical head. of the KNT. This is not just a straight angle on the side of this gear. It's actually a helix, and it's got a very specific degree angle on it, which calculates out a lead, and then that calculates a ratio, and the DRDRO will do this. I will be able to use this vertical head or this universal head really, to machine helical gears, and I'm really excited to give that a try. Maybe sooner than I think, but we'll see. I got to find some time to do that too. But I think that's going to do it for this video. This was a lot of fun. I still have some work to do on that mounting plate. Maybe make a splash guard for that servo motor, because once I start cutting metal, I'm going to want to use the oil, lubricant, coolant. So I still have some work to do to make this complete. Anyway, I hope you liked the video. If you're not a subscriber, hit that subscribe button. It doesn't cost you a thing. But if you would like to support the channel in other ways, you can do that through the links in the description, through PayPal, Patreon, or even channel memberships. Thanks for watching, and we'll see you on the next one.